Why, hello and welcome back to Lecture 8-1 on grid-based mapping with a known pose. As a reminder of our summary and learning objectives, we are looking at occupancy grid maps as a popular approach to representing the environment of a mobile robot in a world given we know the robot's poses. In this approach, we're going to consider each cell independent of each other, and each cell will store a posterior belief that is the probability of whether that cell is occupied or not. Remember, occupancy grids can be learned efficiently by using a probabilistic approach. And then after we talk about the occupancy grids, we were talking about reflection maps, which is an alternative way to represent the world, where each cell stores the probability that a beam is reflected back from that cell. And then we will provide a sensor model for computing the likelihood of measurements and showing that the counting procedure is another way that underlines a reflection map for showing an optimal map of the robot's world. Recall that the content of this lecture comes from probabilisticrobotics.org and the Probabilistic Robotics book, which is written by Dieter Fox, Sebastian Thrun, and Wolfram Burgard. And please check out their website to learn more about their work. So first, let's recall what we learned in Lecture 8-1A. In order to represent a map for the world, we learned that each of the cells in the world is independent. So the probability of a given map is the product of the probability of each of the cells in the world being occupied or free. And we could represent this as a four-dimensional vector for a 2x2 map, or as the product of each of the cells being occupied or free as four independent cells. So the way that we would represent this in terms of binary Bayes filter for a static state, which means the world is not changing and we have independent cells, is that giving sensor data 1 to t and poses of the robot from 1 to t, we can estimate the map by using the probability of this map giving that sensor data and the robot pose is really just the product of the probability of a certain cell being occupied or free, given the robot sensor data or robot pose, where we call that our binary random variable, which can only take on values of 1 or 0. So we can then say that this is the static state binary Bayes filter, where given sensor data and pose data, we can now write this using the Bayes rule as the probability of m given z and x is the probability of z given m, z, and x times the probability of m given z and x divided by the probability of z given z and x. And notice that these are all based upon values in the instance of time up to time t. So then using our Markov independence assumption, we can rewrite this as the probability of m giving the sensor and pose data is the probability of z given m and x only for the current time t, because we are also assuming that the current cell values are not dependent on previous cell values because it's static, and that the probability of m given z and x over the probability of z given z and x. And then we can use another Bayes rule in order to write that first term in the numerator. So now we have the probability of a map giving the sensor and pose data for the robot as the probability of m given z and x times the probability of z given x times the probability of m given z and x over in the denominator the probability of m given x times the probability of z given z and x. So I'm going to skip some of the steps, but what you're going to see what's going to happen here is we're going to look at a way to continue using assumptions in order to simplify this down to something more tenable to make it easier for us to use recursion in order for us to create the map. So using the occupancy update rule and something that we call the odds ratio, we can then simplify this expression down to the following. The probability of m given z and x is 1 minus the probability of m given z and x. And what this means, it's the ratio of the probability of that cell being occupied over the probability of that cell not being occupied. And since a cell can only take on values of 0 or 1, this is why we can write this as the probability of m given z and x over 1 minus the probability of m given z and x. The benefit in writing it like this is we only have to find that one value in order to solve for the recursive method, and this is why it's called the inverse sensor modeling. So we now can rewrite this in terms of using the sensor data, a recursive term, and the prior belief about the map. So use of the sensor data would be the probability of m given z and x over 1 minus the probability of m given z and x for one cell in the world at the current time. We don't have to look at previous times. The recursive term is now the probability of that cell in the map given the values for z and x up through 1 to t minus 1 over 1 minus the probability of that cell m from z from 1 to t or t minus 1. And then finally, the prior is represented by 1 minus the probability of that cell being occupied over the probability that that cell is occupied. We can now write this as the following to update each map cell. The belief at a certain time that a cell is either occupied or not can now be written as the inverse of 1 plus 1 minus the probability of m given z and x over the probability of m given z and x times the probability of m over 1 minus the probability mt times 1 minus the belief at t minus 1 that a cell is occupied or not over the belief at t minus 1 that that cell is occupied or not. So another way of expressing this that makes it a little bit easier to solve is to take the log of that previous expression. The benefit in doing this is now all of those products and divisions becomes addition and subtraction, which may be a little bit more easy to calculate in a computational model. So then you would have the log of the probability that I have a certain occupied cell in the map given the sensor and the robot's pose is the log of mi given z and x at the current time, the log of mi given previous values of z and x minus the log of ni. So that's now our inverse sensor model, our recursive term, and our prior in terms of the log odds form. So this can also be written as the following to update the cell, where the inverse sensor model takes in the map cell, the current pose of the robot, the current sensor data, plus the log of those values at that cell at t minus 1 minus the initial value of that cell L naught. So when updating the occupancy grid map, the idea is that you update each individual cell by using a binary Bayes filter and then use the fact that the map is static to solve. So here we have that formula, the belief that at a certain time at XY we have an occupied cell. Now using our binary Bayes filter, we have our normalization constant, and the probability of a sensor value given a map at a certain time is the integral of the probability of that map given the previous value of that cell in the map and the motion model as an input times the belief of the value of that cell times dm. But since the map is static, we can get rid of the integral and just write this as the belief that a certain cell is occupied or not is the normalization constant times the probability of a sensor data given that that value of that map times the belief of the value of that map cell at t minus 1. So the occupancy mapping algorithm, which can be highly efficient because it now, if you look at the log odds form, it only depends on computing sums and differences, is the occupancy grid mapping where we pass in the log at t minus 1 for a certain map and we pass in the sensor data and the pose for the current time, is for all cells. If mi is a perceptual field of z, then lt minus 1, you pass that into the inverse sensor model, and then mi, x, and z minus the initial prior belief. Or if it is not, then you just say that the log of ti is the same as the log of t minus 1i. So you keep it as the previous value if the sensor data does not inform you that it is in the perceptual field. And you do this, and then you return at the end the log of ti for that particular cell. So here's what the inverse sensor model looks like. If you have a robot with a sensor on it and it has some beam width, then you would consider cells along the optical axis of the robot, which is the red line. So anything that returns a value, then you would make that occupied. So anything in between the robot and that maximum range on the beam is going to be a white because those cells are assumed to be not occupied unless it reflects back here at the end. So we now say that the sensor in the middle has a linear model, but we use a Gaussian distribution in order to represent everything else along the curve of the beam. And if it's outside of the range of the sensor, then it's gray. So it's either white for free, black for occupied, and gray for prior belief of 0.5. We don't really know. So here's what this looks like where you have an occupancy value depending on the measured distance. First, we have our prior belief here, which is 0.5, which means we have no info, and this represents the gray area outside the range and beam of the robot. And then for our free areas, this represents the areas where nothing was reflected back or the beam did not hit anything. So you now decrease these values, this is Z minus D1, to something below 0.5. Then the measurement Z was right here in the middle. And so then Z plus D2 would represent anything that the robot was able to detect. And so at that measurement, Z plus D2 would represent anything that was occupied, which is now above 0.5. And we have no info. So now distance between the sensor and cell in consideration are all these distances where we then can make decisions about whether it's free, it's occupied, or from our prior belief, it's still 0.5, which means we really just don't know. So the update for the sensor data depends on the measured distance and the deviation from the optical axis. So we say that the data is linear in terms of the sensor because that goes down that center axis there. And then theta is Gaussian in deviation, which is theta. So we call xt the pose of the robot. D is the distance at an angle theta, where y would be anything that is straight down the y-axis from the robot. And so we now can represent this as ml or md theta given the robot's pose, which is the likelihood of a cell being occupied based upon reading from the sensor data. And so this is what this is look like. It's a sphere of influence of the sensors where we have the measured distance along one axis. Along the other axis, we have theta, and then the vertical axis is the probability. And what you should see is that it takes on this Gaussian shape here, where if theta is 0, and that means it's directly down the axis, it's right in the middle, and it may have a maximized value, but then it kind of curves off in this Gaussian fashion based upon the beam width, where, you know, at some points it may be outside the sphere of the beam, so we just don't know. So that middle value would be around 0.5, for example, if you don't know. And then as you maximize up here, this is the very center of the axis, so there's a higher probability that those cells are occupied. But when it starts to drop off, it's either we don't know or we know that cell is free. So it's the Gaussian for one arc, where the probability of a map index given sensor data is given by deviation from the primary axis. And here's another example that's a combination of a linear function Gaussian with typical motion models for occupancy grid. So once again, you can see that it takes on this Gaussian shape where a cell with no prior belief, or we just don't know, is 0.5. And then if the cell is free, it starts to dip down, which is what you're seeing here in the middle. Or if it starts to spike up, then we can say that most likely there was something occupied right there, where you have the spike for these two different examples. And so what happens is that as the robot moves through the world, it's going to have an initial belief of maybe 0.5 for every cell in the world. Then as the robot moves around, this robot took 18 measurements. So every time the robot moves and takes a measurement, it's now adding all of these measurements together. And after the 18, using the log odds approach, here is the robot's map of the world as an occupancy grid showing occupied space and free space. And here's what it looks like on the robot. So as the robot continues to move, it is showing darker spaces for where it's estimating there is a cell occupied. It shows white space if the cell is free. And there are a few areas where it goes through some walls here. And then there's some gray areas, which means that the prior belief was not updated because the sensor could not detect anything. So it didn't know if something was occupied or not. So then how do you clean this up? So the way you clean this up is by using a maximum likelihood map, which is obtained by clipping the occupancy grid at a threshold of 0.5. So if you notice, the difference between the left and right map is all the gray areas are gone. So that essentially says if it's above 0.5, it's just black. If it's below 0.5, it's just white, or the unknown area stays unknown outside, but it cleans up all of this over here and it assigned them a value that was either black or white, but no gray. And this concludes lecture 8-1B on grid-based mapping given a known pose for your robot. There's one more lecture in this series. It's lecture 8-1C, and it is on reflection mapping. I hope you're learning a lot. I hope you enjoy. I hope you watch more than once, and I hope you're clicking those like buttons if you're really following along and enjoying this. Once again, thank you for coming and spending time with me, and have a robotacular day.